All right. Good evening. Um, my name is Deb Marr. I'm a professor of ecology at Indiana University South Bend, and I'm serving as the moderator for tonight's talk. The Our Universe Revealed lecture series includes talks in science, music, and the arts. So, STEAM for everyone. We feature current research and creative work that's being done in our region, and it's an opportunity to be curious about ourselves, our world, and our universe, which is the topic of tonight. This is a partnership with the St. Joseph County Public Library, Indiana University South Bend, and also the University of Notre Dame. Tonight's speaker is Roman Gerasimov. He did his undergraduate degree at the University of College in London with a degree in astrophysics. Come on in. We've got plenty of seats. Come forward. Well, you could join us for a really interesting talk. um, And Roman holds a doctoral degree from the University of California at San Diego. He was awarded the prestigious International Astronomical Union's 2023 PhD prize for his research in stellar physics. The International Astronomical Union PhD prize recognizes it's a global recognition for outstanding scientific achievement in astrophysics, and this was for his doctoral thesis work. One of his hobbies is mountaineering, and he's climbed many of the 14,000 peak mountains in California. And his research interest is on old stars that formed shortly after the Big Bang, back when the periodic table was still under construction. And so he is part of the Even Kirby's group at the University of Notre Dame. He's part of the Galactic Archaeology group, and that's something fun that I got to learn this time. I didn't even know there was archaeology of stars. So I'm really excited, and we will get started.
Well, thank you so much. All right. You guys should be able to hear me. I think I can hear myself, so that is a very good sign. Right. So, thank you so much for the introduction. It's a great pleasure to be here. The term galactic archaeology was already mentioned, and it sounds a little bit weird. Sometimes I call myself a galactic archaeologist. So, before I talk about the James Webb Space Telescope, which the title of my talk is promising, and before I talk about old stars, I would like to introduce my field. What is galactic archaeology? What does it mean to be a galactic archaeologist? So the way I usually describe what is it that I do for a living when people ask me is I start with a hypothetical question. Imagine that you wanted to make a car from scratch. How many elements of the periodic table would it take? Most people would immediately think that iron is important, and that's probably the case because cars are made of steel, and iron is a fundamental component of steel. But it turns out that this analysis has actually been done a few years ago. People measured the exact elemental composition of a typical car. And the answer to this hypothetical question is that you're going to need virtually the entire periodic table. So if you start thinking about catalytic converters and batteries, you're going to need, even though in small amounts, but nonetheless very important elements, some of which I cannot even pronounce. The reason why I'm bringing this up is to point out that virtually everything that we know, cars, humans, cats, astronomers, exists because of the incredible chemical diversity that the universe today has. All of those elements of the periodic table exist, they all have different properties, and you can combine them to make exciting things. And it is really easy to take that for granted, but this has not always been the case. Now, if you go back in time about 14 billion years, and you look at the universe when it was still a baby shortly after the Big Bang, the periodic table was very boring back then. It only had two elements, hydrogen and helium, and nothing else, because those are the only two elements that could be produced by the Big Bang directly. So you couldn't have cars, you couldn't have astronomers, you couldn't have cats. And what happened then is over the course of 14 billion years, stars have created the rest of the periodic table. And my job as a galactic archaeologist is to determine how this process occurred, how we went from this primordial and boring soup of hydrogen and helium to the incredibly complex, chemically diverse universe where cars can exist. And the reason why we call this galactic archaeology is because it is actually similar to conventional archaeology. Now, I don't know anything about conventional archaeology, even though I will be drawing this analogy a lot in this talk. So I'm probably going to butcher it, so I have to apologize in advance. But what I think archaeologists do is they go out there and they look for ancient artifacts and then they study them and they try and figure out how human civilization came to be. And if they can find a lot of these artifacts and they can figure out what time period they belong to and what their properties are, then they can figure out something about what kind of civilization existed at the time. And this is exactly what galactic archaeologists do, except instead of looking for ancient artifacts, we look for very old stars. So my job is to go out there and look for old stars in the universe, determine how old they are, and to measure their chemical composition. And if I can do that, then I can begin to put together not the history of human civilization, but the history of the periodic table. Now, the periodic table has approximately 100 elements. They all have their own fascinating stories, and many galactic archaeologists study a lot of those elements. But in this talk, I am going to focus on one element in particular, and that is oxygen. Part of the reason is because oxygen is very important for our existence. It's a fundamental ingredient in water. It's also in the air we breathe. But also, it is a bit of a low hanging fruit, which is why I chose to focus my PhD thesis on it. And I will explain the reason why that is the case in a few minutes. But the takeaway here is that my job is to find all stars and determine their chemistry. And so the next logical question to ask is where exactly are you going to find all stars, especially where are you going to find all stars in large numbers? And this brings me to the second part of this talk. And I would like to introduce my favorite astronomical object, a globular cluster. What is it? And now I think it's been mentioned that I am a postdoc at Notre Dame. For those of you who don't know what that means, it is a purgatory between grad school and what they call a real job, with all of the responsibilities of a full-time professional researcher and none of the job security. Before I was a postdoc at Notre Dame, I did my grad school at UC San Diego in California. And there's a couple of things that you can do in San Diego that you cannot do in South Bend. First of all, San Diego is surrounded by a lot of desert, and the desert is very dark, which means that you can see a lot of stars. It would only take you about 40 minutes to get into the desert from the city of San Diego, and in order to get skies that are equally dark, here in the Midwest, you would probably have to go all the way to the Upper Peninsula of Michigan. And that was a huge advantage. Here's a picture of me looking at the sky from the desert. Something else that you could do in San Diego is you could look at some parts of the southern sky, because San Diego is a bit further south than South Bend. And so, if the time of year is right, you'd be able to see at least a part of the southern sky that you would not be able to see from the latitude of South Bend. And so, here's a picture of me looking at the southern skies from San Diego in the desert. And that star that I highlighted in this slide looks a little bit fuzzier than the rest. There's a very bright naked eye target. And it turns out that if you look at that star with a pair of binoculars, then you would realize that it's not just one star, it's actually a whole bunch of them. It's like a whole sphere of stars, all densely packed together. So this is something astronomers call a globular cluster. It's a cluster because it's a cluster of stars. It's just like a family of stars that presumably have the same origin, they form from the same environment, and they live together. It's like a mini galaxy within our galaxy. It's globular because it kind of looks like a sphere. There are approximately 150 of those in the Milky Way. This particular one is called Omega Centauri. It is actually the brightest one, which is why you can see it without a telescope, just by going out into the desert. This particular globular cluster has about 10 million member stars, so that's a lot. But the reason why I'm talking about globular clusters in this talk is because most of them tend to be extremely old. The age of Omega Centauri, this globular cluster here, was estimated as anywhere between 11.5 to 13.5 billion years. For context, we believe that the age of the universe is approximately 13.8 billion years. So if you take the upper bound of that range, then Omega Centauri may contain the oldest stars that currently exist. Those stars formed pretty much immediately after the Big Bang. And so if you are looking for old stars, which is what galactic archaeologists do, then globular clusters are an ideal place to go. So to draw this analogy with conventional archaeology a little bit further, looking at a globular cluster is a little bit like finding the ruins of an ancient library. or instead of having just one artifact that you can study, you get a whole bunch. And most importantly, they are homogeneous. If you are looking at an ancient library in Greece, then presumably everything that you find in that library was produced at approximately the same time. So you don't have to worry about different time periods mixing together. And presumably, most of the texts in that library are going to be in Greek because they were produced by the same civilization. Likewise, all of the stars in the globular cluster presumably have the same origin because they're all one big family of stars. They all form together, they are traveling together through the galaxy. So they probably have similar ages and they probably have similar chemical compositions. And so you can, at least naively, you can think that you might be able to get rid of all of those additional complexities and study this simple, uniform population of stars. So I promise that this talk is going to be about oxygen. And so what I would like to talk about next is how exactly you go about measuring the oxygen content in the stars in a globular cluster. So let's take Omega Centauri again as an example, and let's zoom in. This is actually a picture of Omega Centauri taken with the Hubble Space Telescope. This is just a tiny, tiny fraction of the cluster. There's a whole bunch of stars here. Some of those are bright, some of those are faint. The reason why they have different brightnesses is because they have different masses. So in general, heavier stars are going to be brighter, and lighter stars are going to be fainter. And this is why you have such a diversity of brightnesses. And what I'm going to do is I'm going to do something that was first done by Isaac Newton some 400 years ago. So this is literally a technique that is as old as physics. This painting demonstrates a famous experiment that Isaac Newton performed at the University of Cambridge, where he demonstrated that if you put a prism in the way of sunlight, then you're going to see the entire rainbow of colors that that light is made out of. And this must have been truly a groundbreaking discovery because the person in the background looks utterly terrified and it looks like they're running for the door. But this is exactly what I'm going to do. I'm going to pick a bright star within Omega Centauri. I'm going to pick that bright red star. And I'm going to decompose that light into the whole rainbow, so all of the colors that go in. Astronomers do not use the same type of prism that Newton used multiple centuries ago. We use more complicated devices called spectrographs, but the fundamental principle behind it is exactly the same. And what I'm going to do then is I'm going to zoom in even further. I'm going to pick a particular fraction of that rainbow, specifically a part of that rainbow near a specific shade of orange that I want. And I'm going to zoom in even further. And if you zoom in, then it becomes very apparent that some of the colors are actually missing from that rainbow. So there is a whole bunch of these black lines that are simply gone. Like there is, like that specific shade of orange is missing. And this is very important because the reason why those lines are there is because those specific shades of orange have been absorbed by different elements within that star. Every element has a unique set of colors that it can absorb. And the reason why I zoomed in this particular part of the rainbow is because of that one very special line there, because that line is actually due to oxygen. So the oxygen that is inside that star is absorbing, removing, getting rid of that specific shade of orange, and this is why that black line is there. And presumably, if you have more oxygen in your star, then that line is going to be more prominent because there's going to be more absorption of that color. If you have very little oxygen, that line is going to be mostly gone because if there's not much oxygen to absorb that color, then that color is still going to be in the rainbow. So this is what that might look like. Here I have two different so-called spectra, so the rainbows of two different stars. One of them is oxygen-rich, the other one is oxygen-poor. And if you trace this oxygen line with your eyes, then the oxygen-rich star clearly has that line far more pronounced than the oxygen-poor star where you can barely see it at all. And so in principle, you could measure how pronounced that line is and you can determine the abundance of oxygen. And for globular cluster, this was done, to my knowledge, for the first time in 1979. And it has been done many, many, many times since for many different globular clusters for lots of stars. And the conclusion has almost always been nearly the same. But before I tell you what this experiment shows us, I'm going to talk a little bit about what we would naively expect to get from this experiment. Naively, we would expect that all of the stars in a globular cluster should have approximately the same chemical composition. Just like once you uncover an ancient library, you would expect all of the text there to be in the same language because presumably that library was produced by the same civilization. However, this is not at all what we see in globular clusters. It turns out that in virtually all globular clusters, you can sort of divide all of the stars into two subpopulations. There's going to be a group of stars that are extremely oxygen poor, and there's going to be a group of stars that are comparatively oxygen rich. And the difference between the two could be as much as a factor of 10. So there could be 10 times as much oxygen in some stars compared to others. And this is really unexpected. So if I were to draw this comparison even further with conventional archaeology, it's like uncovering a library and then looking at the books that are contained within that library, and a lot of those are in Greek, but there's also a whole bunch of books that are in some early Chinese script. Now, this is very surprising. This is not something you would expect, and that this would make you reconsider everything you know about the history of that civilization. And this is exactly where we are with globular clusters. This is the so-called issue of multiple populations, the idea that most globular clusters contain multiple chemically distinct populations of stars. And even though we have known about this for over 50 years now, we still do not know why that happens. There isn't a single theory that can self-consistently explain how an apparently simple population of stars, such as those in a globular cluster that share the same origin, for some reason, would have drastically different chemical abundances. Now, there is one big caveat. The experiment that I mentioned, where you decompose the light of a star into a rainbow and you look at a particular line and the like, this can only really be done for the brightest stars in those globular clusters. That's the reason why I picked a particularly bright star for this example. If you picked a much fainter star, for example, that star over there that you can barely even see, your rainbow is going to be very, very faint, because you're going to take a very small amount of light that that star is emitting already, because it's faint, and you're going to spread it really thin across many, many, many different colors, and you're just going to have nothing left. You're not going to be able to see that oxygen line anymore. And so, even though we have known about multiple populations for a very long time, most of the experiments that dealt with multiple populations were based purely on bright stars. And bright stars are stars of higher mass. So they were based on stars that are some of the heaviest stars within those globular clusters. It has been assumed for the longest time that low mass stars would have multiple populations as well. But we didn't really know if that was the case because we could not do this type of analysis. We could not take their spectra and we could not measure the intensities of oxygen lines within those stars. And so, as a graduate student at UC San Diego, I was looking for a problem that I could potentially address. And in general, if there is something that hasn't been measured and you can find a way of measuring it, then you might learn something new and that might be a potential step forward. And so, even though it has been assumed that low mass members of globular clusters would have the same chemical patterns, it was not known. And so, I was looking for a way of measuring it without doing spectroscopy, because those stars are just way too faint to do the analysis that I just described. And that is what the next part of my talk is going to be about. So the aim here is to figure out how to get oxygen abundances from those faint low-mass stars within the cluster that you cannot do spectroscopy on. And in order to proceed, I'm actually going to give you guys a very quick lesson in physics of stars. So you can imagine any star. It could be the sun. You can pick any favorite star. And that star does two things. Well, actually, it does a lot of things, but it does two things that I care about in this talk. First of all, it's emitting a lot of light, and that costs some energy. That light is coming from the sun all the time. The sun is by far the most important source of energy on Earth. But also, if you look at the very center of that star, the material in that so-called stellar core is so hot and under so much pressure that hydrogen turns into helium in a process called nuclear fusion, and that produces energy. All right, so you have these two processes. You're losing energy because the star is radiating light, and you're making new energy through nuclear fusion. And stars exist in this balance between these two processes. Astronomers call that energy equilibrium, such that stars don't really change over time. Right? All of the energy that you lose is replenished by this nuclear fusion, and the overall brightness of the star and the overall temperature remains more or less the same. And this is good news, as if the sun kept constantly changing its brightness, we probably wouldn't be here. So I would like to represent that with a plot. That's going to be the only plot that I'm going to look at in this talk. So if I were to plot the brightness of a typical star in the y-axis and the time that has passed since that star formed until present day, then that would be the x-axis. Then for a typical star, that plot is just going to be a straight line. right? Because you have this energy equilibrium and nothing is really changing. This particular line is for a star that has a mass of about 30% the mass of the sun, which is actually very close to an average star you're going to find in the globular cluster. And we start 13 billion years ago because globular clusters are old, and then we evolve all the way to present time, and nothing really changes. Now, if I picked a slightly lighter star, for example, a star that's about 10% of the solar mass, there's going to be a little bit of change in the beginning when the star is young and still trying to figure out what's going on. But eventually, it's going to still find its energy equilibrium, and you're still going to get a flat line because this is what stars do. Now, that star is going to be fainter because, in general, lower mass stars are fainter, but it's still going to have more or less constant brightness throughout its entire existence up until it dies. And then weird things happen, but we're not going to talk about that. But if you keep reducing the mass of your star even more, and you take it down to about 8% of the mass of the sun, then this behavior changes drastically. Because once you get too light, there will not be enough pressure and there will not be enough temperature in your core to sustain nuclear fusion. And nuclear fusion is going to turn off. And the energy equilibrium is going to be broken. Your star is still going to radiate energy away, but it will not be able to replenish it. And so instead of maintaining constant brightness for billions of years, your star is going to be cooling down and it will be gradually getting fainter. And this is exactly what this line is showing us. Instead of a flat line, it is now a constant decline. In fact, most astronomers would not even call this object a star. In general, the standard definition of a star requires it to undergo nuclear fusion. If it does not, then it's something else. So it is not really a star. We have a special word for this type of object. We call it a brown dwarf. It's sort of a star-like object that is too light to undergo nuclear fusion. And so instead of shining constantly with unchanging brightness and unchanging temperature, it is gradually cooling down and it is becoming fainter. And the reason why I'm bringing those brown dwarfs up is because it turns out the exact rate at which they are cooling is going to depend on how much oxygen they have. So if I were to do this plot for two different brown dwarfs, one of which is oxygen rich and the other one is oxygen poor, you are going to get slightly different plots, and these stars, or rather brown dwarfs, are going to end up with slightly different brightness at present day because they have different abundances of oxygen. And potentially, if you could measure those brightnesses, then maybe you could infer the abundances of oxygens inside those brown dwarfs. There are many reasons why this dependence exists. Perhaps one that I find most fascinating is actually related to water. These brown dwarfs are cool enough for water vapor to exist in their outer layers. And since oxygen is a key component in the water molecule H2O, an oxygen-rich brown dwarf is going to have a lot of water, and an oxygen-poor brown dwarf is going to have a whole lot less water. So you can think of those two brown dwarfs as a H2O-rich one and an H2O-poor. And water, or rather water vapor in the atmosphere of a brown dwarf is going to do the same thing that water does here on Earth. It's going to effectively act as a blanket that is going to slow the cooling process down, and it's going to allow that brown dwarf to remain warm for a little bit longer. And so as a result of that, you are going to get different brightness at present day for brown dwarfs of different oxygen abundances. And so what I wanted to do is I wanted to try and utilize this feature, the ability to measure oxygen from brightness alone, in order to see whether multiple populations that have previously been known to exist among bright high-mass stars also exist for the lowest mass members of globular clusters, including brown dwarfs. The problem is that brown dwarfs are extremely faint, right? So this 10% solar mass star was about the faintest star that you could observe at the time when I started my PhD. So this was the faintest limit with the Hubble Space Telescope. So anything that's fainter than that, Hubble Space Telescope would not be able to see. And these brown dwarfs, even though the oxygen-rich one is slightly brighter than the oxygen-poor one, they are way fainter than the faintest star that could be observed at the time. So when I started my PhD, there wasn't a single telescope that could see those brown dwarfs in globular clusters. And then throughout my PhD, things drastically changed. And that would be the next and the final section of my talk. As finally, we are getting to the James Webb Space Telescope. So this is what James Webb looks like. It was being assembled before it launched near Los Angeles. And I actually got to see James Webb before it got launched. I was one of the few people who got invited to have a look. But unfortunately, because Northrop Grumman, which is the company that was doing the final assembly stages, is a military contractor, they had a strict no photography policy. So I did not take that picture. I found that picture on the internet. And there are two things about JWST that make it particularly suitable for looking for brown dwarfs in globular clusters. First of all, it is really big. It was so big that there wasn't a single rocket that it could fit inside, and the engineers had to do this whole origami thing where the telescope was folded in inside the rocket and then it had to deploy itself once it got out into space. But this is actually less important to me than the other important feature of this telescope. This is an infrared telescope, so it does not observe normal light, or at least that's not its primary purpose. It sees infrared light, and brown dwarfs tend to be much, much cooler than regular stars. And generally, cooler objects emit more infrared light. And so, in the eyes of JWST, brown dwarfs would be much brighter and way easier to observe. That is actually the reason why the mirror of the telescope, which is what you see in the middle of this photograph, looks yellow. It's because it was gold coated, because gold is a better material for reflecting infrared light. James Webb was launched on Christmas Day around 4 a.m. Pacific time in 2021. This is a picture of me watching the launch. I was very stressed because the outcome of my dissertation depended on it. Had James Webb turned into a $10 billion firework, I would have had to figure out something else to do for my PhD. But fortunately, that didn't happen. The launch went as successful as it could be, and that whole origami experiment also worked out well. And eventually, James Webb was deployed. And about a year after that launch, my collaborators and I got to point it at a globular cluster in order to look for brown dwarf members for the first time. So the globular cluster that we picked for our search for brown dwarfs was this globular cluster here. This is NGC 6397. It is one of the closest globular clusters to us. It's actually the second closest. There is a globular cluster that's slightly closer, and it might have been a better choice, but it's also placed behind a cloud of dust, and so that introduces additional complexities that we didn't want to deal with. And to us, this second closest globular cluster, which is something like 8,000 light years away, seemed like the best choice. And then you have to pick which part of the globular cluster you are going to observe, because JWST can only see a small fraction of that globular cluster. We ended up picking that specific part in order to observe with JWST, and the reason why we picked that part is because it was observed almost 20 years ago with Hubble Space Telescope, and it is actually important to observe the same part of the globular cluster twice, and I will explain why that is in a moment. So now I'm going to show you the picture of this globular cluster NGC 6397 that we got. It's going to be the only image from James Webb Space Telescope that I'm going to have in this talk. And here it is. And I'm just going to take a short break. Okay, so this is a lot of stars. There's also a whole bunch of galaxies in that picture. So all of those like fuzzy spots, like that guy, this guy, those are background galaxies that have nothing to do with the globular cluster. They're outside of our galaxy. They're behind all of those stars. And that brings up an important question. If you are going to look for brown dwarfs in this image, then the first thing that you need to do is you need to determine which of those stars are members of the globular cluster, and which of those stars are either not stars at all, but background galaxies, or perhaps stars that are in the foreground and just happen to be in the same part of the sky. And they really have nothing to do with that globular cluster. They are just photobombing the shot. And this is why it is important to observe the same part of the globular cluster twice. Because if you have two different observations, then you can figure out from the shifts in the positions of individual stars in which direction they're moving and how fast. Right? So if you compare the Hubble image from 20 years ago and the James Webb image that we got, then you can figure out where those stars are going. So here's a cartoon representation of that. So you're going to have a whole bunch of stars, and some of them are going to be members. So those are represented with red, and some of them are going to be non-members. So they just happen to be in the same part of the sky. Those are represented with blue. If you observe this globular cluster twice and you work out the velocities of all of those stars, then presumably all of the members, all of the red stars here, they will be moving in approximately the same direction and with approximately the same speed because they all belong to the same globular cluster, so they're all traveling through our galaxy together. On the other hand, all of the stars that just happen to be in the same part of the sky and are completely unrelated to the globular cluster that you're looking at, they're going to have random velocities. There's no reason why they should be associated with the velocities that the globular cluster has in any way. And so if you do this exercise and you look at all of the stars and how they move between Hubble and James Webb images, you can determine which of those are members and which of those are not. So this is kind of fun to do, which is why I have this animation here. It shows a very tiny portion of the field of view that we managed to get from that previous image that I showed you a couple of slides ago. And it blinks together the Hubble image from 20 years ago and the James Webb image that we got. The Hubble image is the one where the spikes near the stars are vertical and horizontal. So Hubble Webb, Hubble Webb, Hubble Webb, Hubble Webb. Okay. So this is a galaxy. It's a spiral galaxy. It has nothing to do with the globular cluster. It's in the background. It's really far away. It's not going to move between those two images. It's way too far away for that, so it pretty much remains in the same position. So that is expected. Now, that is also a galaxy. James Webb can see it clear as day, and Hubble cannot because it is way too faint and way too red for it. And even though it has nothing to do with the globular cluster, I like to point it out because to me that really demonstrates just how much better of a view of the universe we get with James Webb. Like that galaxy, as far as Hubble concerned, doesn't exist. Now, most of the stars, so if you look at this group of stars here, they're kind of shifting in that direction there. And we can assume that that is the overall velocity of the globular cluster, and so all of those stars are members. Right, so if they're moving in roughly the same direction, then they're probably associated with each other. They're gravitationally bound. But there are exceptions. So if you take a closer look, you might find, for example, that star there, and it seems to be moving in a completely different direction. So that star is not going in the same direction, and it's also going significantly faster than the rest of the stars, and so that is probably not a member. And it is important that we don't confuse that for a brown dwarf in that globular cluster because that star is not in the globular cluster at all. And so you have to go through this exercise with all of the stars, and there are thousands in this field of view of James Webb. But in the end, you can filter all of these stars that you see out, and you can specifically focus on just the stars that you are absolutely sure are members of this particular globular cluster. And what you do then is you look for the faintest of all of those members, and presumably some of those are going to be brown dwarfs. And this is exactly what we did, and we ended up finding 3 brown dwarfs in this globular cluster. And they are highlighted with green circles. They are extremely hard to see because they're super faint. In fact, I would almost certainly bet that you would not be able to see them in this picture, which is why I also have zoomed in cutouts of all of those 3 brown dwarfs. Right, so there they are. It is extremely faint compared to all of the stars next to it. Those are some of the faintest objects that we can detect in this globular cluster. We know for a fact that they are members of that globular cluster because their velocities match with the overall movement of the globular cluster. Their names are actually their approximate temperatures that you can estimate from their colors. So this guy here is 1600 degrees Kelvin. This guy here is 1400 degrees Kelvin. Now, this is pretty hot by human standards, but this is very, very cold by stellar standards. And this is the reason why things like water vapor can exist in the outer layers of these objects. But the question that you might be asking is, like, what does that tell us about multiple populations? Like, are those brown dwarfs oxygen poor, or are those brown dwarfs oxygen rich? Before I proceed, I would like to also point out that because globular clusters are some of the oldest objects that we know of, astronomical objects, those brown dwarfs are probably the oldest brown dwarfs that we know of, which is kind of cool. So those aren't just the first brown dwarfs in a globular cluster ever discovered, they're also the oldest brown dwarfs that we know of, at least out of those that we can estimate the age of, which I think is kind of cool. But to me, what I think is more important is not the fact that we found 3 brown dwarfs, but it's the fact that we only found 3 brown dwarfs. As far as formation processes are concerned, brown dwarfs are exactly the same thing as stars, except they're slightly lighter. So there is no reason why brown dwarfs should be produced at a slower rate than stars. If you have a lot of stars in a globular cluster, you should also have a lot of brown dwarfs. But we only found 3. There are thousands of stars, but we only found 3 brown dwarfs. And perhaps the reason why that is because those brown dwarfs tend to be so faint in their majority that even for James Webb Space Telescope, it is not sufficient to be able to detect them. And only a small minority of brown dwarfs are bright enough in order to be detected. So in this case, only 3 out of however many brown dwarfs could have been in this field ended up passing our membership cut and ended up on this slide. And so remember, if we go back to the diagram that I had earlier, if you look at all of the members in the globular cluster, some of them are going to be oxygen rich and some of them are going to be oxygen poor. And you can tell that by the strength of their oxygen lines, at least with high mass stars. The version of that diagram for brown dwarfs is going to be that perhaps if they are displaying multiple populations in the same way as their high mass counterparts, then you're going to have oxygen rich brown dwarfs and oxygen poor brown dwarfs. And the way you tell them apart is that the oxygen rich ones are going to be relatively bright and the oxygen poor ones are going to be relatively faint. Except it looks like the overwhelming majority of brown dwarfs in this globular cluster are extremely faint. We only found 3 that were within our range. So it looks like all of the oxygen rich brown dwarfs, or at least the vast majority of them, simply do not exist. And so at this point, I am fairly convinced that multiple populations do not exist in brown dwarfs, at least not in the same way that they do in higher mass stars. It looks like the population that is oxygen poor is overwhelmingly dominant when it comes to low mass stars compared to their higher mass counterparts. And this is really strange. So I'm going to hammer down on my conventional archaeology analogy. So let's say that you found this ancient library and you look at it and you expect most of the books to be in Greek, but a whole bunch of them are in some early Chinese script, and this is really confusing. You don't know why this is happening. And then you build a new shovel, and this is a bigger shovel than you've ever had before. It costs $10 billion. It's coated in gold and it can see infrared light. And you dig deeper and you discover that that library actually has a whole extra floor that you weren't aware of. So that floor represents low mass stars and brown dwarfs. And then you look at the books that are present on that floor that you just discovered, and it looks like virtually all of them, with the exception of 3, are written in some early Chinese script. Now, this is really, really strange. Now, why this is happening, I'm afraid I cannot give a definitive answer because with just 3 brown dwarfs, that's a small number statistic, and it's going to be a wild speculative guess. But I can, at the very least, give you that. I can make some educated guesses. So what I think happened is that the oxygen-rich population of stars and brown dwarfs in this globular cluster formed first, and some of them were big and some of them were small. So those will correspond to stars that are bright and stars that are faint, and some of those faint stars might actually be brown dwarfs if their mass is sufficiently low. And I anticipate that when those oxygen-rich stars and brown dwarfs were forming, the environment in the globular cluster was somewhat chaotic, and so they ended up scattered all over the place. And then over time, things calmed down a little bit, and the environment stopped being as chaotic as it was when the globular cluster was extremely young. And perhaps the oxygen poor population formed a little bit later. Maybe some of the oxygen rich stars died, and from their ashes, a second generation of stars emerged. But because by then the environment in the globular cluster has calmed down quite a bit, you would expect this second generation of oxygen poor stars and brown dwarfs to be much more compact and much closer to the center and arranged in a much neater way. And what's going to happen then is this globular cluster is going to exist for 13.5 billion years in order for it to get to present day, and it's going to lose some of its members. And it turns out that, first of all, if you are light, it is much easier to get lost because it's easier to eject a small object from a globular cluster than a big one. So the big one is tightly gravitationally bound to the rest of the cluster, and the small objects are less so. But also because this initial oxygen-rich population is less centrally distributed, it is more chaotic and more random, there are more of its members closer to the edges of the globular cluster, and it would be presumably easier to get rid of them as well. And so preferentially, what you would be losing is small, low-mass members that belong to the oxygen-rich population that formed earlier on. And so if all of those blue stars that represent the oxygen-rich population that are also small and brown dwarfs eventually get ejected from the globular cluster, then you're kind of left with what you see today. All right, so when it comes to high mass stars, because they're very difficult to eject either way, you're going to see an even mixture of oxygen rich and oxygen poor members. But when it comes to low mass stars and brown dwarfs, you're not going to see a whole lot of oxygen rich members because the majority of them just got ejected over the course of 13.5 billion years. Now, again, this is a speculative guess. It is based on just 3 brown dwarfs. We're going to need a whole lot more in order to be able to determine the exact statistics of it and figure out what is actually going on. So I'm going to move on to the final slide of my presentation, which is again a picture of me looking at Omega Centauri. And I would like to close this talk with just 3 comments. And perhaps some lessons that I learned from this whole study. The comment number one is that this is the very beginning of the journey. We didn't really learn much about multiple populations per se from the small sample of just three brown dwarfs. What we did is we discovered a new way of looking at globular clusters in the first place. Throughout most of the history of research into globular clusters, everything we knew about their chemistry came from high mass stars that could be measured spectroscopically. Now, with James Webb, we have the ability of probing globular clusters much, much deeper and observing objects and measuring the chemical composition of objects that simply could not be done before. So, this is the very beginning. There's a whole lot more to be done. We could look at the same globular cluster, NGC 6397, again. We could look at other globular clusters, and we could build the sample of brown dwarfs in globular clusters that we know of from three to some much larger number that would allow us to do much more rigorous analysis and perhaps make a more significant step forward in this mystery of multiple populations that we still do not understand. The second comment that I would like to make is that everything is more complicated than it seems. The reason why globular clusters were so interesting to study to begin with is because people used to think that they were simple. It's the idea that all of the stars are coming from the same environment, so they should have similar chemistry, similar ages. But that is clearly not the case because we have these multiple populations, and not only do we have multiple populations, it looks like they vary depending on the masses of those stars as well. And in some sense, this is frustrating, but also without that complexity, I would not have my job, so I cannot complain too much. And the last comment that I would like to offer before I close this talk off is that we uh, live in a really good time as far as astronomical research is concerned. Most globular clusters are fairly bright because they have a lot of stars. A lot of globular clusters are easy naked eye targets, such as Omega Centauri, right there. Which means that people have looked at those globular clusters for thousands of years. Now, I don't know if this is the case or not, but they do say that the Hadrian's Library, which is the library that I was showing pictures of, had approximately 20,000 books. And I would be willing to bet that at least one of them mentioned some of those globular clusters. But we didn't know anything about their chemistry until 50 years ago, give or take. And we got the ability at looking at brown dwarfs in those globular clusters less than 2 years ago with the launch of James Webb. So if you look at a plot of our knowledge of globular clusters since they were first discovered by humans, which would have happened many thousands of years ago. It was a flat line, just like a star in energy equilibrium, and then over the last 100 to 50 years, there was a sudden spike, and it looks like it's going up exponentially. So I'm very grateful to be alive today. So that is the reason why I have that job, and it was a privilege to share the state of affairs in this field with all of you. Thank you very much.
Questions?
You said the closest global cluster you tried to get to, you couldn't because there was a cloud dust or something like that?
It's not necessarily that we couldn't. We actually applied for James Webb Time to look at both of them, and we are just now getting to the data on the other globular cluster. That was M4, which is slightly closer, but it is somewhat obscured by dust, and you need to correct for that when you're doing your analysis. So that is what I'm actively working on right now. NGC 6397 is almost entirely dust free, the line of sight to it, so it's a little bit easier to analyze.
When you're looking at one of the missing bands in a spectrograph, you said the band we were primarily talking about today was oxygen. Is that purely elemental oxygen? Can you see bands from oxygen that's bound in molecules as well?
Yes, you most definitely can. So molecules tend to have much more complicated structures than atoms, and so they have a whole lot more lines. And so in general, there are so many lines in those molecules that they all kind of merge together. And instead of seeing individual lines, you sort of see giant chunks of the spectrum missing. And so that is, for example, exactly what water does. So water just removes huge chunks of the spectrum, and water is one of the molecules that bears oxygen. In general, it is a little bit easier to analyze a single line compared to like a whole bunch of lines that might include possibly millions, if not billions, of lines with more complicated molecules. But yes, molecules also create spectral features that can, in principle, be measured. They're just more complicated to deal with.
I was curious about your hypothesis that the oxygen-rich stars formed first. Um, do you have a thought about why that might be? Since it seems like it would more likely be the other way around.
Well, so based on just this result here, the fact that we seem to be missing oxygen-rich brown dwarfs, or at least they are present in far smaller numbers than the oxygen-poor ones, suggests that it would have to happen in that order, right? Because you would expect that when the globular cluster originally forms, it's sort of a giant cloud of gas and dust that collapses. And as a result of that, your stars are going to be very energetic and they're going to be moving around. But then when the second generation of stars forms, it's going to be happening from presumably bits and pieces that the first generation of stars ejected, and those would not be moving anywhere near as fast, and so they would be far less likely to be ejected. But I'm not sure if that answers the question.
So I was just thinking about, if the cluster formed in the very early universe, before there had been time to form a lot of oxygen.
Oh, okay. I see what you mean, right? So naively, you would think that the abundances of all of the elements should be increasing. But that actually does not have to be the case because those nuclear reactions that produce elements, they could be a little bit more complicated than that. So that could go either way. When you get some kind of process of nuclear processing where you just convert your abundances from one state to another, some of the abundances can be going up and some of the abundances can be going down. They do not necessarily have to be uniformly going up. So that oxygen might be converted into something else. It might be diluted by something else. So there's a whole bunch of various theories out there that would describe how you would reduce the abundance of oxygen whilst increasing abundances of other elements. Yeah.
So the oxygen, is this something that was produced inside the star by the fusion process, or is this something that was captured from, say, a large giant star that went supernova early in the formation of the globular cluster? So where did the oxygen in the star come from?
So in the case of globular clusters in particular, the most likely origin would be actually material ejected off large stars. Right, so some of the stars in the globular cluster when it first formed would have been like absolutely massive, and generally massive stars have very short lifespans, so those stars would not be around. And so in the process of their death, oxygen would be produced inside of them, and then it would be somehow delivered to the surface, for example, with convection. And then it would be ejected from the surface of that star. And so this enriched material is going to then repopulate the globular cluster, and then the next generation of stars can form from it.
So then the amount of oxygen that would be captured when the dwarf forms would be partially due to the size of the supernova that ejected oxygen, or to be part of the formation of the dwarf, right?
Yes, it probably was not necessarily a supernova. It was probably a slower process. Um, but yeah, so in general, it is the massive stars that produce elements that are heavier than hydrogen and helium. And so it would have been those massive stars that only existed in the early history of the globular cluster and then all died off that would have been responsible for all of that chemical enrichment.
So then the distribution of the oxygen that you're seeing with what stars you can find, would that basically give you some historical perspective on the size of the stars that blew off the oxygen that got captured by?
Yep, that's absolutely the case. So people are trying to construct models that would predict how this chemical enrichment occurs. And one of the input parameters into those models is the distribution of masses of those stars that undergo nuclear fusion that produce all of those elements. And so, in principle, you could reverse engineer those out. And this is one of the reasons why we're struggling to explain multiple populations, is because none of those models are self consistent. They all have some internal contradictions. So, for example, you could have a model that requires a certain mass of a star to produce the oxygen abundance that you are seeing, but there isn't enough mass in the globular cluster to produce that star. This is the so called mass deficit problem. This is one of the issues that we're dealing with. But in general, yes.
Oh, just a classic. What's next? First of all, congratulations on a wonderful presentation.
Oh, thank
I
you.
really enjoyed that. So, are any of the do you think any of the fainter brown dwarfs would be available through longer integration times on that? And are any of the brighter brown dwarf targets eligible for spectroscopy?
I don't think we'll be able to do spectroscopy on brown dwarfs anytime soon. Those things are far too faint. But the limiting factor right now is actually not James Webb itself. I sort of overlooked that part in the talk, but we needed Hubble images in order to do membership selection. There are fainter objects in the field than the brown dwarfs that we have confirmed.
We've done exoplanets. We've seen spectroscopic signals from exo brown dwarfs. So
Oh, that these things are very far away.
yeah.
That's the problem with globular clusters. They are so distant. Yeah, we know of lots of brown dwarfs that we have spectra of in the solar neighborhood that are nearby. The challenge with globular clusters is that they're much, much further away. Right? But the next thing to do would be, instead of using archival Hubble data for membership selection, is to observe those globular clusters with James Webb multiple times, several years apart. In fact, we already have proposals in to do just that. And then you would be able to lift the restriction that Hubble imposes, and you'd be able to determine whether those fainter objects are members or not. And I'm sure that some of those are going to be brown dwarfs.
You said 8,000 light years for this one?
I think that's the distance to 6397, yes.
Yeah, in the fuzzy area, actually. Yeah.
Yeah, we have discovered a few brown dwarfs at kiloparsec distances in the field with James Webb already. Yeah, but I doubt that we'd ever be able to do spectroscopy, at least not in the near future, with distances that are involved in globular clusters.
So the New Worlds Observatory.
Maybe. It would need to be much bigger.
So how do you estimate the age of a brown dwarf or any? So some of the stars are saying 13.5.
Right, so this is a very good point. So, in fact, we considered brown dwarfs themselves as an age metric for globular clusters, because unlike stars that maintain constant brightness, brown dwarfs cool down over time. And so, depending on how faint brown dwarfs in the globular cluster are, you should be able to estimate the age of the globular cluster. But in general, the way you estimate ages of globular clusters is using high mass stars, actually. As I mentioned, answering your question previously, in general, the higher the mass of a star is, the shorter its lifespan is going to be. And so all of the truly high mass stars that existed in globular clusters at some point in the past, they have all died out. So the high mass stars that I was referring to in my talk, they were like actually comparative with low mass stars. They were just much higher mass stars than the brown dwarfs are. So depending on what the highest mass of a star you have in a globular cluster that is alive today, you can figure out the approximate age of that globular cluster, because anything that's higher mass would have died already. And so if you know the lifespan of those objects, then that is a direct estimate of the age of the globular cluster itself.
Are there any other questions? Does dark matter play a part in your research?
That is an excellent question. So there is a different category of an object that is sort of similar to globular clusters. It's also a bunch of stars that are gravitationally bound and they're traveling together. They're called dwarf galaxies. And some of the dwarf galaxies might actually be smaller than some of the larger globular clusters. But the fundamental difference between the two is that dwarf galaxies have dark matter content in them, and globular clusters do not. That is sort of the definition that astronomers draw in order to differentiate these two types of objects. So globular clusters in general do not have dark matter in them, and so uh, it does not factor in my work. Yeah.
Yeah. Just quickly, how do you determine the temperature of your dwarfs? Yeah, I noticed that you had the Kelvin temperature was used as the naming.
You do that primarily based on their color. You can construct a computer model of how a brain dwarf of particular mass is going to evolve and what sort of color it is going to have at a given age. And then if you know the age of the overall globular cluster, then you can compare that to the colors that you see. Generally, the redder you are, the colder you are. Yeah, this is a very approximate estimate. Ideally, you would like to be able to get a spectrum of that thing, and that
Yeah.
the strengths of certain lines depend on the temperature. But in the absence of that, yeah, from the color, you can get a first order estimate of the temperature.
Okay. Okay.
Any other questions? How permanent is this to get time on the James Webb Telescope? Like, what is that process like?
You can apply for time once a year. There are cycles that are 1 year long. It is in general extremely oversubscribed. Um, I think it is something like a factor of five, approximately, more oversubscribed than the Hubble Space Telescope used to be at its peak. And I think in this most recent cycle was actually more than a factor of five. But the first couple of cycles were a little bit less oversubscribed. It was a little bit easier to get time on James Webb back then. And so I suspect that I had an easy time getting those observations approved. But yeah, in general, it is very competitive. It is open to anybody in the world. You do not have to be affiliated with NASA. You do not even have to be affiliated with an American institution. You can apply for James Webb time from anywhere, and so long as your case is compelling enough and you can convince multiple reviewers that it is compelling enough, and more compelling than all of the other proposals that are being submitted, you can get time on James Webb.
And how much time do you actually get when you're talking about time on it? How much observable?
So for the image that I showed you, that was approximately a 2 hour long exposure. So we pointed James Webb at that cluster for 2 hours. And it is something that I didn't mention, but I think it is quite remarkable. The Hubble image that I also showed that we used for comparison, that image took 200 hours.
Mm.
Yeah.
If I could just make a comment, the James Webb Space Telescope is the first telescope that we had, double-blind selection. So names get taken off
Mhm.
proposals. And what we found immediately in the first year was the diversity of people, including young scientists, that were more to time. And so, I mean, I think you're an example of the success of that. And I'm really, it's really wonderful to see this data being used.
Yeah, the reviewers do not know who you are.
This is the first one that's true. Yeah, so
Right.
the Nobel Prize winner, they take the name off a person who's postdoc. It's all the proposal.
Yeah, if you're referring to your research and your proposal, then you kind of have to reduct it and make sure that your name is not mentioned so that the reviewers cannot figure out who you are. That's one of the rules. Yeah.
So if you could take a 200-hour exposure using the James Webb Telescope, would you be able to capture enough light to possibly do a spectral?
Then again, I do not think so because I think the gap is just way too wide. But with a 2 hour exposure, you're going to be able to detect a whole lot more brown dwarfs. And so you'd be able to derive more statistics based on just their brightness and colors.
You got to come up with more compelling things so you can get more time.
It's much harder to get 200 hours in James Webb than 2 hours, especially given that uh, 2 hours was sufficient for the science case that we have, which is just detecting any number of brown dwarfs. Yeah.
How widely are those images shared once they're obtained? You asked for 2 hours, you got the images from those 2 hours. Were those also made available to other astronomers around the world to draw conclusions from?
Yeah, you get 12 months to do whatever you want with your data privately, and nobody else gets to see it except for your collaborators. Once that timeline expires, the data becomes available to everybody else. There is a website you can go on, you can download all of the James Webb data that has passed that 12-month uh, private access period. Yeah, that is done so that you can claim any discoveries you want without too much competition, but you kind of have to be fast.
Well, okay, let's think. Wait.
All right. So that was wonderful. It's great to see other places. So this Friday, there will be the Christmas lecture. Dr. Michelle Thaler will be giving this talk at the Sentry Center. She is right here. And so she's the director of science communication at NASA's Goddard Space Flight Center. The talk will be at the Sentry Center, so pretty much right across the street. And so that will be this Friday, 6:30 p.m. And then in the spring, we will be starting back with the Our Universe Revealed lecture series. We'll be starting the first week of February. And you can take a look at the website here. So if you just type in Universe Revealed, University of Notre Dame, you'll pull that up and you can see previous talks that have been taped. So if you've missed any and you want to catch up, you can do that. And then we'll be starting back in February. So thank you so much for coming, and we'll see you in the spring, if not this Friday.